In the Hello students, in the last lecture we have solved the Phin equation for two different boundary conditions. One was the fin with insulated tip and the other one was the fin with infinite length. Then we are going to define two important performance parameters in this lecture. The performance parameters are fin efficiency and fin effectiveness. Along with this, we are going to talk about the proper length of the pins and the corrected length of the pins. So in this lecture I'm going to cover the pin efficiency, its relevance, pin effectiveness and its relevance, what is the meaning of proper length of the pins and what is the meaning of corrected length of the pins. So this is going to be the agenda for this particular lecture. I am Nitin L. Birud, working as Associate Professor in Sandeep Institute of Engineering and Management. Now let us discuss about the fin efficiency. You might be able to recall that two lectures back I have shown you ideal fin in which there is no resistance for the heat to flow due to conduction. Means the thermal conductivity of the fin was infinite. And in that case, there was no drop in the temperature when the heat was flowing into the fin. This is the limiting case. There is no resistance, zero thermal resistance or infinite thermal conductivity. The temperature of the fin will be uniform at the base values. Whatever is the temperature of the base, it will remain same over the entire length. Let me show you an example. Suppose the base temperature is 80 degrees Celsius and the fin is ideal. So everywhere at any point of time under, of course we are dealing with the steady problem. So at any point of time, at any location along the fin, the temperature is going to remain the constant. This is of course the ideal condition. But actually the heat transfer from the fin will be maximum in this case, of course, because the temperature variation is not there. So we can get maximum amount of heat transfer, and that can be expressed with a simple equation that is once again obtained from the Newton's law of cooling itself. H into P into L. P into L indicates the lateral surface area of this fin, perimeter into length, into theta b. We know theta b means the temperature difference between the surface and the fluid. Now everywhere the same temperature difference is there, and that's why, and that is equal to theta b. So we are taking theta b. So it is nothing but H into surface area into delta T. So this is Newton's law of cooling, and that is what is called as maximum heat flow from a given fin under ideal situation. Of course, if there is no temperature drop, but in reality, however, the temperature of the fin is changing. We have seen already along the length of the fin. We have calculated also for the numericals, and this was this is actually the condition. The temperature at the base is 80. At some distance, it might be 70, 65, 61, 58, 56. Now, it depends on what is the thermal conductivity of the material. Okay, so these values may differ for different materials. Okay, and this is what is called as actual temperature variation in the fin material, and thus the heat transfer from the fin will be less. Of course, in this ideal condition, it is going to have maximum heat transfer rate, and under this real situation, because of the variation in the temperature along the length, the rate of conduction, rate of convection at different location is different, and because of that, the rate of heat, the rate of heat transfer from the total bin is less because of the decreasing temperature, and this parameter which relates these two, that is the rate of heat transfer in actual condition to the rate of heat transfer in ideal condition, is called as fin efficiency. So let us define it. To account for this effect in the decrease in the temperature of heat on heat transfer, we can define a efficiency term, and the efficiency is defined as actual rate of heat transfer from the fin to the ideal rate of heat transfer from the fin if the entire fin is at base temperature. If the entire fin is at base temperature. So what is going to be the heat transfer from the fin when entire fin is kept at the same temperature? That is what is called as ideal condition. The thermal conductivity of the material in that case Q. is infinite and there is no thermal resistance offered for the conduction. So that's why their entire surface is maintained at the same temperature, and that surface that is equal to the base temperature of the surface. So this is the definition of fin efficiency. Now we can put it in terms of equation, that is Q fin divided by Q fin maximum. So for a fin with insulated tip, we already derived the expression for Q fin, and in the last slide we have written the mathematical form of Q fin max. So if we take the ratio of these two, that is the equation 3.16 and 3.19 in the last slide, then we will get this equation, that is Q fin upon Q fin max for a fin with insulated tip is equal to tan hyperbolic ml upon ml, tan hyperbolic ml upon ml. And if the same calculations are repeated for a fin with infinite length, so using equation 3.15 and 3.19, you can get efficiency of the fin is equal to Q fin upon Q fin max is equal to 1 upon ml. So it was tan hyperbolic ml upon ml for a fin with insulated tip, and it is only 1 upon ml for a fin with infinite length. Okay, so this is about fin efficiency. Now, basically, what is fin efficiency? It is actual heat transfer rate to the maximum possible heat transfer rate. Means it is comparing the performance of the actual fin with the ideal performance. Let us see some of the other aspects. An important consideration in the design of the fin surface is the selection of proper fin length. This we are going to discuss at the end of this. What is the meaning of proper fin length? But normally, this is possible that longer the fin, the larger is the heat transfer area, and thus higher is the rate of heat transfer. This is what we traditionally can think, that longer the fin, larger area is available for the heat to get transfer, and that's why we'll get more rate of heat transfer. But also, larger the fin, bigger is its mass, higher the price for the material, and then more is the fluid friction. Means if we are increasing the length of the fin without worrying or anything, what is happening is the weight of the system is going to be more, the cost of the system is going to be more, and the operating cost of the system, because of the increase in the fluid friction, which will give rise to the uh, what you call pumping power, is going to be high. So that longer fin, although it may give us the results in the terms of higher rate of heat transfer, but it is at the cost of more weight, more price, and more operating price or operating cost. Therefore, increasing the length of the fin beyond certain value cannot be justified unless the added benefits overweights the added cost. So if you are getting additional benefits because of the addition in the length, if you are getting more benefits, then of course it is suggested to go for those benefits. But if your whatever length increase is not giving us and it can be justified against the added cost of the material, then it is not justified or it is not suggested to use that length of the fin. Now fin efficiency help us here. Also the fin efficiency decreases with increasing the fin length. Now this is also true because fin efficiency is the ratio of actual rate of heat transfer to the maximum rate of heat transfer. Under maximum rate of heat transfer, you assume that the fin length along the fin length the temperature is same, but actually the temperature is dropping. It means that along the length we are moving from the base to the tip. There is reduction in the rate of heat transfer continuously. So the fin efficiency will be reducing. So if you are increasing the length, automatically the overall fin efficiency is going to be less because the rate of heat transfer is continuously on the reducing side. And because of this, because of decrease in the fin temperature with the length that cause fin efficiency to drop below 60%. Now this is very important. The lengths normally that causes the fin efficiency drop below 60% cannot be economical and shall be avoided in practice. So you have to calculate simply the what is the fin efficiency. If you found that for a particular length it is less than 60, avoid that length. If it is more than 60, then that can be at least considered for the analysis further. Otherwise, you can ignore that. The efficiency of the most of the fins, normally we are using very highly conductive materials, thermally conductive materials for the fins to be manufactured, like copper, aluminium, and that's why the efficiency of the fins is more than 90%. So almost all the pins which are used in the practice are satisfying this particular criteria. Of course, if they are not satisfying the criteria, there is no need to use this type of pins. So this is the relevance of the pin efficiency. Okay. Then we will define another term called as pin effectiveness. Fins are used to enhance the heat transfer, that is known to us. Why we are putting the fins? Intention is to increase the rate of heat transfer. The use of the fins on the surface cannot be recommended unless the enhancement in the heat transfer justifies the added cost and complexity associated with the fins. What type of complexity? Increase in the fluid friction, basically increase in the weight, increase in the maintenance, maybe because of the presence of the fin. If no fins are there, the surfaces are clean, can be easily cleaned, easily removed, or easily maintained. But if the fins are there, you can just imagine the cylinder of our vehicle, the two-wheeler vehicle. Can you clean that cylinder from the outside easily? No. We need some specific equipments for removing the dust. Even we are not removing it normally, but just I'm taking you example that the simple addition of the pins is giving us more complexity with the system. It increases the weight of the system and it increases the cost of the system. So fins use is not recommended unless and until all these things are getting satisfied. We already seen in the last slide also for fin efficiency. In fact, there is no assurance that adding the fins on the surface will increase the heat transfer. Already I have in the first lecture also about the fins, I told you that there is no guarantee that when you are putting the fins, that is going to result into some heat transfer increase. That we have to calculate, we have to ensure this through the calculation. That insurance is obtained with the help of this term called as fin effectiveness. Let us see. The performance of fin is judged on the basis of enhancement of the heat transfer relative to the no fin case. If the fin is not there, what is the rate of heat transfer? If the fin is added, what is the rate of heat transfer? Compare them. If you are getting that addition of the fin is resulting into some increase in the rate of heat transfer, good, very good. So can we put it in terms of simple term, and that term is called as fin effectiveness. So the performance of the fin expressed in terms of fin effectiveness, and effectiveness of the fin is defined as the ratio of Q when the fins are there and when fins are not there. So if fin is there and if fin is not there. So let us see what is the meaning of this diagrammatically. This is the fin and some heat is getting transferred. So we already written the equation for this term Q fin. Now what is Q no fin? If the fin is not there, how much area is exposed in the absence of the fin? Of course, this other area, whatever was there, was already exposed. So it will continue to the transfer of the heat. What is changing when we are putting the fin? We are blocking this much area only. That area is equal to the cross section area, and from this area whatever was the heat transfer rate, okay, it is supposed to increase because of the addition of this fin. So we are going to compare the rate of heat transfer from the fin from the to the rate of heat transfer when there is no fin, means the area from the area which is equal to, you can see here, the cross section area of the fin. So let us calculate it. When where Q no fin represents the rate of heat transfer from the area if no fins are attached to the surface, that is the cross sectional area of the fin. How to calculate it? So Q no fin is equal to H into area, Newton's law of cooling I am writing, area into TB minus T infinity, that is theta B. TB minus T infinity is nothing but theta B. So where AC is the cross section area of the fin at the base, and this is our equation for Q no fin. So if you use this equation once again for effectiveness, you can write it in this fashion: Q fin divided by H AC into theta B. TB minus T infinity is equal to theta B. Now if you use this for the fin with insulated tip, then we'll get the equation Q fin upon H AC into theta B, and the results are solving, after solving you'll get under root Kp into HAC into tan hyperbolic ml, and same the calculations they are repeated for a fin, infinite fin, we'll get the results Kp into HAC under root Kp into HAC. So these are the results for fin efficiency and fin effectiveness for fin with insulated tip and fin with infinite length. We are going to use them while solving the numericals. Now, what is the physical significance of the effectiveness? Let us once again come back to that term, basic term. Forget about the equation now. Q fin divided by Q fin, Q no fin, sorry. That is the Q from the cross sectional area of the fin. Means why the fins are put added? They are added for increasing the rate of heat transfer. So what is expected? Actually, there must be more heat transfer rate as compared to the no fin case. It means that the value of effectiveness shall be always more than 1. So let us find out what is the significance of these things. If effectiveness of the fin is equal to 1, it means that Q fin divided by Q no fin is equal to 1, which indicates that the addition of the fin on the surface does not affect the heat transfer. Do not The fins are not needed at all. If you are putting the fins and if you calculate the fins effectiveness is equal to 1, there is no need of the fins. Forget about it. Don't spoil your surface. Don't increase the cost of the system. Don't increase the weight of the system. Not at all suggested. If the fin effectiveness is less than 1, very bad case, even bad than this, that fin actually acts as insulation. Why we are putting the fins? For increasing the rate of heat transfer. But actually what we are getting? Reduction in the rate of heat transfer. This is practically possible. Don't think that this how it is going to be there. We can have a practical case in which effectiveness can be reduced to less than 1 value. And this situation can occur when the fin is made up of low thermal conductivity materials, or if the fin is placed in a location where heat transfer coefficient is very high. If you just revisit, I'm just going back to the last slide to show you the equation. See this equation. Effectiveness of the fin is proportional to the thermal conductivity. Higher the thermal conductivity, more the uh, effectiveness. Then it is inversely proportional to the heat transfer coefficient. It means if the fins are used in a location where heat transfer coefficient is high, say for a condensation and boiling operation, then you are not going to get the effectiveness. So it is suggested always to use the fins only when the heat transfer coefficient in that location is less. And about the geometry, if you take this ratio, perimeter upon area of cross section, so what we can say, that effectiveness of the fin is proportional to this ratio, perimeter upon area of cross section. So fins should have larger perimeter and smaller cross sectional area, and that's why you might have seen that whenever we are putting the fins, we are putting a very small thickness fin, large width but small thickness. The reason is increase in the perimeter with reduction in cross sectional area. That is the theme. That is the idea. And that's why slender fins are going to give us better effectiveness as compared to thick fins. So always go for the thinner fins with larger widths so that we can increase the value of this perimeter upon area cross section term. So let us go back to the significance of the effectiveness. Already seen that it is epidemic, and fins are effective only when if the effectiveness is greater than. It indicates that the fins are enhancing the rate of heat transfer as expected, as it is required. Normally, however, the use of the fins cannot be justified unless the fin is sufficiently larger. Effectiveness of the fin is sufficiently larger than 1. It's not only 1 or 1.5, 1.2. No, it is not going to be useful for. It should be higher, maybe 10, 15, 20, 30, like that. So if that much effectiveness is there, then the use of the fins is more can be more easily justified, cost wise, weight wise, and every other aspects. So that's why this effectiveness, a single term, is very important term for the calculations of the fins, for understanding the concepts of the fins. So now let us talk about the last but one point of this lecture, that is the proper length of the fin. What is the meaning of proper length? By here, what I am going to do is we are going to compare the fin with insulated tip, that is the real fin. Normally we are having this type of fins in practice. Of course we are not actually insulating, but the fin tip area is very small, so those fins can be considered as the real fins because they are having finite length. Okay, and we are going to compare it with the results of infinite length fin. Now what length of the fin can be considered as the infinite length? That is our point. So we are interested in finding out at what length of the fin can be considered as infinite. So let us do it simply. An important step is in the design of the fin is to find out the appropriate length of the fins once the material and the cross sections are specified, and this is what is actually happening in the fins at certain length. See, initially the rate of heat transfer is more because of the higher temperature difference. Then at certain lengths, because of the lesser value of temperature difference, it is very small, and after certain length, it is going to get zero. So what is that length? Where the fluid temperature is equal to the surface temperature of the fin. Okay, that temperature, that length, we have to find out. We'll be tempted to think that longer the fin, higher the rate of heat transfer due to surface area, but actually it is not. But temperature drops along the fins is exponential and reaches to T infinity at some length. Beyond this length, the heat transfer is zero. Already I have told you. Therefore, designing this extra long fins, whatever is beyond this, suppose this length, whatever is this length, additional length, is not giving us any transfer, and this is a material waste. This is going to increase the weight, increase size, and increase cost, and with no benefits in the return. So what is that length? Let us find out. To get the sense of proper length, we compare the heat transfer from the fin with finite length, that is with insulated tip, that is equation 3.16, and to the heat transfer from the infinitely long fins, that is equation 3.8, under same conditions or same fins, only the length is different. Let us compare. We are already having Q fin with insulated tip, this is the equation, and Q fin with infinite length, this is the equation. So this bracketed term is same, Tb minus T infinity is also same. If you take the ratio of these two terms, we will get tan hyperbolic. So Q fin insulated divided by Q fin infinite is equal to tan hyperbolic ml. What is the meaning of this? When I am saying Q fin insulated means the actual fin, and Q fin infinite means the infinite fin. So when a actual fin will behave like an infinite fin, when the rate of heat transfer from the actual fin is equal to the rate of heat transfer from the finite fin, if the value of this tan hyperbolic ml is equal to 1. If it is equal to 1, it means that the actual fin rate of heat transfer is equal to rate of heat transfer from the infinite fin, and that value where tan hyperbolic ml is equal to 1, that value of L is the infinite length of the fin. So let us put it in a tabular fashion. The value of tan hyperbolic ml are evaluated for some values of ml, and the results are given in the table. So this is our table. You can see that we have taken ml is equal to 0.1 and tan hyperbolic ml was found to be 0.1. Similarly 0.2, 0.3, 0.4. What is the meaning of this tan hyperbolic ml? Now let us put this value here. Let us take this, say 1. When ml is equal to 1, tan hyperbolic ml is 0.762. I am just putting it here. Here 0.762. So Q fin actual is equal to 0.76 into Q fin infinite. Means actual fins performance is 76% matching with the performance of infinite fins. Means the length of this fin in this particular situation of tan hyperbolic ml is equal to 1 is 76% matching with the infinite length. Now let us increase it to 1.5, 90% matching, 2, 96% matching, 2.5, 98% matching, 3, 99.5% matching, 4, 99.9% matching, and 5, 1. Means at ml is equal to 5, we are getting tan hyperbolic ml is equal to What it means that when the length of the fin is corresponding to ml is equal to 5, means when the length is of the fin is equal to m upon 5, then that length can be called as fin, infinite length of the fin. If you plot the graph of that time hyperbolic ml versus the ml, then you will get this type of things. Initially it will increase, and then it will become, increase is going to be slow, it become asymptotic, and then it will become constant. So at almost 5, you'll get it is becoming constant. After that, it will remain 1 throughout. So if you increase beyond 5, be useless, because that is what is called as fin with infinite length. But practically, let us see, heat transfer from the fin increases with ml almost linearly at first and reaches to the value of infinite long fin at about ml is equal to 5. So therefore, fin length L is equal to m upon 5 is can be considered infinite long. But whether that much fin length is actually required? No. Reducing L by half, that is 2.5, when ml is equal to 2.5, or length is equal to m divided by 2.5, which will reduce the length by half, causes the drop of only 1% in the heat transfer. So what we are getting when we are increasing the length from ml is equal to 2.5 to ml is equal to 5, we are doubling the length. But how much heat transfer rate is improving? Only by 1%. So it is required? No. So can we go for it? No. So what is the correct length? So normally in practice, the fin length, which is corresponding to ml, is equal to 2.65, which gives us 99.9% of the heat transfer, only 0.1% change. And this length ml is equal to 2.65 is considered as the fin width infinitely long. So this, beyond this length, you can easily say that there is no heat transfer in the fins. And this parameter can be used for the comparison with the actual fin with the infinite fins. So this was about the proper length of the fin. Now we'll learn about some other concept called as corrected length. You may recall that in the first lecture, rather second lecture of the fins, I told you that why we are considering this fin with insulated tip, and when we are removing that insulation, the convection is considered. So we are getting some other equations, and I told you that the equations which are used for the calculations of fin with convection from its end are rather complicated. But we can use the results of fin with insulated tip, and we can just made a small correction into it, and we can use those results with fin in which convection is actually considered. So even we ignore the convection in the calculations, but just with a help of simple correction in that equation of fin with insulated tip, we can use those results as a result of fin with convection, and that correction is called as corrected. Fin subjected to convection at the tips can be treated as fin with insulated tips by replacing the actual fin length by corrected length. Just what you have to do is replace the fin length in the equations of insulated tip with a modified or corrected length. And how to define this corrected length? Very simple equation. Corrected length is equal to L, actual length of the fin, plus area of cross section of the fin at the tip divided by the perimeter at the tip, where AC is the cross section area and P is the perimeter of the tip of the fin. Now what is the meaning of this? Let us try to understand. If you multiply this relation by the perimeter, if you multiply this equation by perimeter, what will you get? LC, that is corrected length into perimeter. So let us call it as corrected area. You will get some corrected area. Length into perimeter is area. So LC into uh, that perimeter is equal to corrected area is equal to P into L, actual length, actual area, surface, lateral surface area of the pin, and this multiplied by perimeter is equal to cross section area. Means what we are getting, if you multiply this equation by uh, perimeter, you will get corrected area is equal to lateral surface area plus cross sectional area. Means Actually, when we are ignoring the we are considering the fin with insulated tip, we are ignoring this area. Correct? Only this much area is considered for the heat transfer. This area of cross section is very small and that was ignored. But when you want to consider this contribution of this area of cross section also, what we are doing, we are putting it in terms of this area of cross section into perimeter as an additional length, and that additional length is added in the actual length to get the corrected length. So that was as simple as this, which indicates that the fin area determined using the corrected length is equivalent to the sum of the lateral fin area plus the fin tip area, that is cross sectional area of the fin. The corrected length approximation gives very good results when the variation in the temperature near the tip is very small, when there is less movement of the fluid near the tip basically, and the heat transfer coefficient at the fin tip is about the same as the lateral surface of the fins. Means if the heat transfer coefficient are for the lateral surface and for the cross section both are almost same, then these approximation results are going to be very good results. Okay, so this is about the corrected length. So in this lecture we have seen what is the meaning of fin efficiency, what is the relevance of the fin efficiency, what is the meaning of fin effectiveness, what is the relevance of fin effectiveness, what is the meaning of proper length, what is the way of finding out the corrected length for making the calculations of the fins simple. In the next class, I'll be discussing about the numericals, the fin. Okay, thank you very much.